Alright, welcome back. This is 4.3, which is the addition and elimination method for 2x2 systems, right? This one, of course, is my favorite when you're doing it of the first three sections in those methods. We saw some pretty severe limitations for graphing. I mean, I'm that limitation essentially, but being able to graph well is that limitation. And then in the substitution, we can imagine that it wouldn't be too difficult to run into an a substitution problem where you just can't avoid fractions from the get-go. So we move on to elimination, and this is where I start typically. That's kind of a lie because I actually do 4.4 almost every time. But if I have to do it in one of these three methods, this would be the go-to for me. So the idea is that we're going to use the addition principle of equalities, which was like chapter 1.1 or 1.3 type material. But it says if you add the same thing to one side and the other side of the equation, you still have an equality, right? What it doesn't say is that it has to be the exact same looking thing, it just has to be equivalent. You have to add something to the left that's equivalent to something you're adding to the right. So let's take a look at how this works. If I have a system, let's say this one, x plus y, very simple to start here, equals 5. And then I have x minus y is equal to negative 3. What I'm saying is that in the second equation here, x minus y is the same thing as negative 3. So if I'm dealing with my top equation, I can add x minus y to the left-hand side of it, while adding negative 3 to the right-hand side of it, and I still maintain that equality. So we can view it as I'm adding these two equations together. If I add my left-hand side, I get x plus x is 2x. And what do you know? Y and negative y is nothing. It's 0, it's gone, and I've eliminated my y. So on the right-hand side, I have 5 minus 3. That's 2. Oh my goodness, look how easy this is. If I divide by 2, I get 1, and I'm halfway done, right? Go back to the last video and look at the first couple of things, the first couple of examples. It took the entire board practically to get to this point, right? This is why I like this method, because if you can get a nice, quick, easy elimination, boom, we're already halfway done. And I just have to take this one, plug it into one of these equations, and solve for y. So into the top equation, I'm going to write 1 in place for x. Plus y equals 5, well, subtract your 1, and you have y equals 4, and we're done already. It's easy, that's it. My solution is 1, 4. Bam, done. Let's look at a few of these. Let's say I have x plus 2y equals 7. And negative x plus 4y equals 11. Okay. Now again, I can add the left-hand sides together and then add the right-hand sides together. And what makes this work out is that these x's are going to be eliminated. We can see that because one of them is a positive 1, the other is a negative 1. So as long as one of my variables has the same but opposite coefficient, then this elimination method is going to work out for me. If I add these, x and negative x is 0, that's gone, see ya. 2y and 4y is 6y, equals 18. Oh, look at that, divide by 6, y is 3, we're halfway done. And it's been 12.5 seconds, right? Take that 3, plug it into one of these equations, doesn't matter which one. I'm going to plug it into the top one. X plus 2 times 3 equals 7. Or x plus 6 equals 7. And if I subtract 6 from both sides, x is 1. And I'm done. My solution is 1, x is first, comma, 3. That's it. Quick, easy, done. Right? Now, that's assuming that we've got this set up in this manner, right? That's not always going to be the case. Let's take look at one of them that is not. Say I have x equals negative 5 halves y. Plus 4. And 3x minus 5y equals negative 13. Not only is it not set up so that one of my x's or y's will cancel out nicely, this y is not even on the same side of the equation as this y is. Right? This one is on the right-hand side, this one's on the left-hand side. So if I add these, it's going to be pretty ugly right from the get-go. So what I want to do is take this first equation and get that y on the right side, the left side, the correct side, right? And so I would really just add 5 halves y. Let's do that here. X equals negative 5 halves y plus 4. So I'll add 5 halves y to both sides. It eliminates it on the right. That gives me x equals 5, x plus 5 halves y is equal to 4, right? And now I've got this fraction I don't really like, so I'm just going to multiply everything by 2 because I can, right? I can come in here and say, hey, multiply everything by 2. Oops, multiply that by 2, right? And that gives me 2x plus 5y is equal to 8, right? Now this is the exact same equation, it's just written differently. So I'm going to come up here, rather than write this a second time, I'm going to erase that top equation and simply replace it with 2x plus 5y equals 8. And reevaluating this, I'm going to get rid of this work here as well, because I'm going to need the space. So I have to do a little bit of work to get this set up, but now my y's, I have a negative 5y in one, a positive 5y in the other. If I add these together, I'm going to eliminate my y's. This gives me 5x equals negative 5, and I am in the zone because x is equal to negative 1. Right? And now that I have this x equals negative 1, I can plug it into one or the other of these equations, or I can plug it into the original equation that I had here. It's not terribly helpful. I'll just plug it into the bottom because why not? So if I plug it into the bottom, that gives me 3x, which is 3 times negative 1, minus 5y equals negative 13. That's negative 3 minus 5y equals negative 13. If I add 3 to both sides, that gives me minus 5y equals negative 10. And then dividing by negative 5 gives me y equals 2. Right? And that's my solution. Negative 1, comma, 2. So I had to work for it a little bit. That one may or may not have been easier to do with the substitution method, right? This method is not always the easiest. But I think the solution, or the substitution method, would probably also be pretty ugly. You know, try it if you want to, though. But we're going to move on. Let's take a look at this one. I have 2x plus 5y equals 8. And I have 3x minus 2y negative 7. Okay. Now, as it's set up, this is nice that I have my x and y on the left-hand side for my first equation and for my second equation, but neither my x's or my y's will cancel out if I add these things together. So I need to manipulate it a little bit. And I'm going to pick the easiest one. I can look at the x's, right? I can get 2x and 3x to be the same but opposite sign, or I can get 5y and negative 2y to be the same but opposite sign. If it's me, I'm going to stick with probably the smaller numbers, the 2 and the 3, as opposed to the 2 and the 5. And what I'll do is multiply this first equation by 3, right? That'll turn my x term up here into a 6x. In fact, if I write that, it's 6x plus 15y equals 24. Now, I want to do the same thing to my bottom equation, but I want this x term to be a negative 6, so I'm going to multiply this guy by negative 2. And it doesn't matter which one I put the negative on. I could have turned the top one into negative 6 and left the bottom as a positive. It doesn't matter. But here I'm turning the bottom into negative 6, so that becomes negative 6x. This is what I want to happen right there, is to have a 6x and a negative 6x. Continuing to multiply by negative 2 gives me plus 4y, and then equals positive 14. And so I'll combine these two together now. The x's are all gone. That gives me 19y equals 38. And it's quick to see, if I divide by 19, the y is 2. A little bit of work, but not a lot. But I got it. Y is equal to 2. And since y is equal to 2, I can plug that into any one of these guys. Let's just plug it into the top one. That gives me 2x plus 5y, and y is 2, equals 8. Or 2x plus 10 is equal to 8. Subtract my 10. Kind of running out of room here, but if I subtract my 10, I get 2x equals negative 2. Dividing by 2, is this off the board? It's getting close. If I divide by 2, this turns into x equals negative 1. Okay. And that's my solution for this one. Okay. So again, we can manipulate an equation where it's not just going to eliminate right from the get-go. We can manipulate it to make one of my variables set up to eliminate. All right, and then of course we have some weird cases that pop up. So let's look at this one. It's always the same weird cases though. I bet you'll never guess that we're about to get a parallel line. Let's say I have 2x minus 5y equals 13, and y equals 2/5 x, minus 13/5. So that bottom equation is a bit yuck. I'm going to turn that bottom equation into standard form. So we'll do that here. Y equals 2/5 x minus 13/5. I'm going to subtract 2/5 x from both sides. And when I turn this into standard form, I don't really care about the plus or minus because I'm going to end up manipulating that anyway. So I'm just going to leave it here as the negative 2/5 x plus that y equals negative 13/5. But I do want to get rid of all these fractions. That's what haunts me in my sleep, is these fractions. So we'll multiply everything by 5. And so I get negative 2x, 5 times y, so plus 5y. The 5's cancel out here, leaves me with negative 13. Right? So I'm going to replace this second equation with its equivalent equation in standard form. That is negative 2x plus 5y equals negative 13. And you'll note that these two look a whole lot like each other. If I combine these together, the x's cancel, the y's cancel, leaving me with 0 equals, and then the 13 and negative 13 cancels, I get a true statement. So in this case, not only are these parallel lines, but they're the same line. And when we have the same line, we have infinitely many solutions. Infinitely many solutions. All right, let's take a look at one more. I'll skip the initial cleanup, and let's say that I have, negative 2x plus 3y equals 10, and 2x minus 3y equals 15. Right? If I combine these, they're already set up to eliminate, but my x's eliminate and my y's eliminate, and therefore I end up with a 0 on the left-hand side, but I end up with 25 on the right-hand side, and this is false. So if I end up with a false statement, these are parallel but not the same lines, and therefore there are no solutions. And that's all of the cases that we'll see. Most of the ones that we see, we end up with one solution. Every once in a while we end up with parallel lines with no solution, or the same line that has infinitely many. Thank you, and I will see you next time for 4.4.